Okay, hey guys. Welcome to the last episode of my high school math fundamental series for Mr. Visconti's grade 12 religion class. And today we're going to go over integral calculus. And chances are you won't learn this in your grade 12 calculus course here, but if you're pursuing anything maths related in university, you will definitely need to know this stuff, man. And if you ask me, it's kind of silly that they're not teaching it to us in high school here, but I'm here to show you anyhow. That is, unless you take AP courses, they do teach it in AP. Right? So, just how our derivative, right? Let me draw a Cartesian plane here. Represents like the slopes of the tangents in our lines here in for our function here f of x, right? Our first derivative will look something like this, right? That is f prime at x. So kind of similar to derivatives. The integral, so it's kind of a funny looking s for sum there. The integral of fx dx, because we've differentiated in terms of x, right, is kind of like the opposite of that. And what it represents, say you take a definite integral. I'll tell you what the difference between a definite and indefinite integral is later, but if you have a definite integral, say from x equals 0 to, let's say this is x equals 4, right? That integral is going to equal the area between the graph of the function and the x-axis. And if it's below the x-axis, it's important to note that it's a negative area. So that's got a negative area. And then whatever after and up to 4, this has got a positive area. So it'll be the kind of sums of the areas, but one of them is negative. It'll be the area between between that interval and the x-axis in some words. Okay. So it's like a function in and of itself, right? You're pretty much asking, okay, what's the area here? That'll be the value of your antiderivative, right? Or your integral here at that specific point. Okay, so I just mentioned antiderivative. What is that? Okay, so integrals you can kind of think of as the opposite of a derivative, right? A derivative you're kind of going down, I like to say, and then an integral you're going up. When you're integrating, you're going up, and when you're differentiating, you're going down, right? So say we have a function here at f of x equals 5x cubed plus 7x, right? If we found the derivative of that, we all know by now it's 15x squared plus 7, right? But if we wanted to go from f of x here to capital F at x, which represents the antiderivative, and what we'd be using for integrals here, we would have to think of a function that when we found the derivative of it would give us that back. So this capital F at x has the property so that capital F primed at x is equal to f of x, right? When you differentiate this, you're going to get that, okay? So let's come up with something here. Okay, so for this first term here, this 5x cubed, we just have to think about it a little bit, right? We know our exponent is going to be 4, right? Because when we differentiate using the power rule, our exponent is going to go down by 1 to get to 3 here, right? And here we can't just have a 5, right? Because if we were to differentiate this, it'd be 4 times 5, and so it'd be 20x cubed. We don't want that. We want 5x cubed. So what do we have to do to this 20? We have to divide it by 4 here. Okay, so 5 over 4. Okay, because when you differentiate it now, you're going to put that 4 in front, and the 4's will kind of cancel and just leave the 5, right? So for the 7x, we're going to do something similar. We know our power is going to be 2, x to the power of 2, right? But we're not done yet because we have a 7 here. We're going to put that 7 over 2, because when we multiply that, when we bring that exponent to the front and subtract by 1, those 2's are going to cancel out, right? And then we're not done, actually. When we find the antiderivative, or integrals in general, we're going to always write this. This c is the constant of integration here. And basically it means we can add any number to this function or subtract any number, but I mean, I guess that's adding a negative number. We can add or subtract any number to this function, capital F at x, right? And we'll still differentiate it and get this, right? Like it could be plus 205, right? That would just differentiate to be 0, and it'd be like plus 0, but you don't really write that, right? So this 205, that's completely arbitrary. I just made it up, right? Like it can be whatever you want. So we just generalize it and say plus the constant of integration here. Okay, great. So let's start with definite integrals here. Definite. Okay, so say we have the function. I'm just going to make something up. Let's say this is x equals 1, and this here is x equals 5, right? So I could kind of make up a quadratic that would represent this graph here. I could say x minus 1, x minus 5 equals y, or y is equal to that. And let me just let fx equal to it. So let fx equal to this, right? But I'm gonna expand it. So x squared minus 6x plus 5. Okay, so that's our function here, right? We want to find now the area kind of enclosed by it up here, right? And that's between 1 and 5, right? We want to kind of find that area, right? So we're going to use integrals here. Okay, so we want the integral from 1 to 5 of x squared minus 6x plus 5 dx, right? Because we have differentiated in terms of x. Okay, not any other variable. So now we're going to find our antiderivative. So for this one in particular, it would be 1 over 3 x cubed, right? Using that little trick we found earlier. And I'll show you more later. A third of x cubed minus 6 over 2 x squared, right? But that's just 3x squared. And then we have plus 5x, right? It'd be 5 over 1x, but like it's 5x. And then we have our our constant of integration. But we won't need to worry about that for definite integrals, and you'll see why in a moment. Okay, and this here, we're finding it between 1 and 5, remember. So we kind of use that notation there. Okay, so what we're going to do is we're going to kind of write this out twice and sub 5 into it and sub 1 into it, right? Like it's like the difference in the area, right? It's like taking this whole area, right? That's the area all the way from 0 to 5, and then subtracting it by this little area from 0 to 1, right? So we're going to do that here. Okay, and this is actually part of 5, so I'll put pink there too. Okay, so we're going to do 1/3 of 5 cubed minus 3 times 5 squared plus 5 times 5. And then we're going to subtract, since it's a difference of areas, I just said, 1/3 times 1 cubed minus 3 times 1 squared plus 5 times 1. Okay, and let's evaluate this. So 1/3 of 125 minus 3 times 25 plus 25 here. And then we're subtracting 1/3 minus 3 plus 5. Okay. And so let me compute this really quickly. Okay, so sorry, let me have 125 over 3 minus 75 times 3 over 3 plus 25 times 3 over 3. And then that's going to be subtract 1/3 minus 3 times 3 over 3 plus 5 times 3 over 3. Okay. So this is going to turn out to be now 75 times 3. I believe that's 225. So let me check that. Okay, yeah, 225. Plus 75 here. Okay, and that's all over 3. Okay, and we're subtracting 1 minus 9, because that's 3 times 3, plus 15, and that's all over 3 as well. Okay, so now we have a kind of bigger thing. 125 minus 225 plus 75 minus 1 plus 9 minus 15, all over 3. So let me punch that into my calculator here. Sorry, I realize I've just made a little mistake here because I got a negative answer for this, which means that this should be under the graph. We're actually going to say the function, because the function that this represents is actually the negative of this. So that's my mistake. And so I'll write it in here. But what we can actually do is kind of bring that over to the front of the integral. So it's like negative the definite integral between 1 and 5 of that function dx. Okay, and then we can just kind of bring it forward here, because it's like a constant multiple, right? I'll show you some other integration rules, but generally, if you have an integral of negative f of x dx, that's equal to negative f of the integral of f of x dx. Or if you had like the integral of 15 f of x dx, that's equal to 15 times the definite integral of f of x dx. Okay. So we've carried that forward now. And when I punch this into my calculator here, I get negative 32 over 3, but that's going to become positive 32 over 3. Okay, and that is the area under this graph between those 2 points there. Okay. So yeah, that'll be our area here in terms of like units squared. Okay, and that's how you compute a definite integral. Okay. Before I continue, I'm just gonna copy and paste some of my integral rules that I have here. So let me do that. So up here now, I have just written down or pasted some of these rules I had here. Okay, so for a particular function, if you have a constant multiplied by it, your antiderivative is just going to be the constant multiplied by the antiderivative of that function, right? And if you have a sum of functions, your antiderivative is just going to be the sum of the antiderivatives of the two functions. If you have 1, you're going to get x as an antiderivative. If you have x to the n, where n isn't negative 1, because then you'd be having the to the exponent 0 when you add 1 to it, right? And you'd be dividing by 0. Right, and we can't have that. So when you have x to the n and n isn't negative 1, you can find the antiderivative by using this kind of formula here. Or it's the same thing as what I've been using is 1 over n plus 1 times x to the n plus 1. Okay? Or whatever constant you had there in the first place. Okay? So for 1 over x, which is x to the negative 1, so when it is negative 1, you are going to have the natural log of the absolute value of x as your antiderivative. And if you have e to the kx here, your antiderivative is going to be e to the kx, because remember when we differentiate this, when we differentiate e to the kx, right? We're going to differentiate and it will become k times e to the kx, because remember it stays the same. You're just multiplying by the derivative of this using the chain rule, right? And we don't want that though, because we want this, right? So we're just going to divide by k and they cancel out, right? So we want that division by k in our antiderivative. Okay. Cool. So now I'm just gonna briefly touch on indefinite integrals here. Indefinite integrals. And for this, it's kind of just like finding the antiderivative for like a little bit more complex functions here. Like, I mean, if you had the indefinite integral of x squared dx, right? You can compute that kind of right off the bat. Say it's 1/3 of x cubed plus c, right? That's the answer to that. So when you take the indefinite integral, you are getting a function back. And when you take a definite integral with the numbers on the s, like this here, you're going to get just a number back, and that number is going to represent the area. Okay, so we have that now. So I'm gonna go over a method. It's called U substitution. Right, and that's gonna help us, find our indefinite integrals here. Okay, so let's take the integral of root 2x plus 1 dx. Right? What's that now? Right? We can't really like go ahead with this because we've got this plus 1 underneath the radical here. Like if it was just root 2x, we could just break it up. Say, okay, root 2 times root x, and then that's like a constant and bring it in front of the integral, right? But no, we can't do that in this case. We would have to use u substitution. So we're going to say, and bear with me here, let u equals to what is under the radical there, right? So we're going to say let u equal 2x plus 1. And so we're going to differentiate kind of both sides here in a way. So we're going to be du now. So du for like the derivative of u in a way is equal to 2, because that's the derivative of this, right? And dx, because we differentiated in terms of x on this side, right? And u on this side, right? That's just a differential notation there. And so now we can kind of say that our dx here is equal to half of du if we divide 2 by both sides here, right? So we can say now half of du equals dx, right? Multiply both sides by 2, you get back to the, so yeah, you're going to want to isolate for dx, essentially, right? So now we can say, therefore, the integral of root 2x plus 1 dx is equal to, subbing in our u stuff here, the root of u times, and then half of du. Okay, kind of put that in brackets there. Okay, and what we can do is we can bring that half to the front, right? So now we just have half of the indefinite integral of the square root of u du, right? So neglecting that for now, but not totally, right? We're just gonna compute this, right? And that should be simple enough to do. So we are going to say, okay, that's like the indefinite integral of u to the half du, right? So 1 over 2 multiplied by, so we're going to bring that forward, but we're going to divide by, what's it called? Sorry, we're going to have 1 over, as our antiderivative here. We're going to have 1 over 2 plus 1 is 3 over 2. Right, so we're going to have 1 over 3 over 2, but instead of saying that, we can just say 2 over 3 here. That's just the reciprocal, right? You're just inverting it. And that's going to be multiplied by u to that exponent. Sorry, 3 over 2, right? Because it's just 1 more, right? Because when we move that there, it's going to cancel, essentially, right? And 1 less, it's going to go down to that. Right, using our power rule if we're differentiating back, kind of, right? So now that's it, right? But we've got to add our plus c, right? But we're not totally done yet because we've got to sub in x because we want it in terms of x here. So we're going to sub in our 2x plus 1 for u again. So we're going to say 1/2 times 2/3 of, what was that again? 2x plus 1? 2x plus 1 to the 3 over 2 plus c. Right, we got to remember our constant of integration here, right? And so it's going to become 2/6 of 2x plus 1 to the 3 over 2 plus c. And so that is 1/3 of 2x plus 1 to the 3 over 2 plus c, right? And if you want to check your answer, you can just differentiate again. And if you get this answer here, you'll know you have done the use substitution correctly. Okay, this is fairly complicated at times. Well, not complicated, it's just you have to kind of know what your u is going to be, right? Like what would make sense to sub in to make u in terms of the problem, right? Like what will help you solve it, right? So we're gonna do another one here. Okay, we're going to say so I guess this would be B, and let's call this A. Okay, the integral of 5x over 4 minus x squared cubed dx. Right? We want to compute this antiderivative or integral here. So, taking a glance at it, I mean, you can pause the video and try and figure it out for yourself, what we would let u be, but I'm just going to give the answer now, and you'll see why it is this in a second. So we're going to say let u equal to 4 minus x squared, right? So if we have this now, and we do what we did before and differentiate both sides kind of, using our differential notation here, we're going to get negative 2x dx, right? And we can divide both sides by negative 2, or multiply both sides by negative 1/2. So I'm going to do that. Notice how I left the x with the du here, right? That's important because we have an x up here, right? It's kind of like you're multiplying this x by the dx, right? Because you can like bring this out of the fraction pretty much, and it means the same thing, right? Like 5 over 4 minus x squared all cubed times x dx is the same thing as saying 5x over all of that dx, right? So we are going to say, therefore now, the indefinite integral of 5x over 4 minus x squared all cubed dx, I'm going to sub in u now, is the integral, we still have 5 up here, over u cubed. So we've got u to the power of 3 down there, multiplied by, so notice we're just subbing in, we're going to sub in this negative 1/2 du for the x, this should be dx, x dx, right? We're going to sub that, sub this into that. And where do we see that? We see it here, right? So, if that makes sense. Hopefully it does. Hopefully I'm actually being helpful right now. Okay, so we are going to do that now. 1 over 2 du. Okay, and notice how this x is gone, right? There's no x here because we use that as part of our replacement kind of negative 1/2 du. Okay, so we can now write this as 1 over u cubed times negative 5 over 2 du, right? And now we can bring that to the front, negative 5 over 2, so negative 5 over 2 the integral, and I'll write this as u to the power of -3 now, du. Right? We've already simplified this problem so much from this, right? But it'll get more complicated again in a sec. Right, so let's compute this integral here. -5/2, the indefinite integral here of, actually, we don't need that. So we're going to have an addition of 1, so it means we're going to be multiplying by a -1/2 here. And that's u to the -1/2, because when you subtract 1 to differentiate it, you're going to get that -3. And when you bring that coefficient in front here, it's going to cancel out essentially, right? Because we don't have a negative u here. If we had negative u there, then we'd have that be positive, right? But it's not. It's negative here. So, and then yeah. Oh, and plus c. So you are going to have now, and that's positive actually, so 5/4, right? And then u to the power of -2 plus c, right? And then just sub in what you made u. So we made u 4 minus x squared, right? So 5/4, 4 minus x squared to the power of -2 plus c. And we can rewrite this again now as 5/4 times 4 minus x squared all squared. We're changing it from negative to the positive since we have it in the denominator now. And plus c. Right? And I suppose I've got time for one more. So let's do a more challenging one, I suppose you could say. Okay, so C. We're going to have the integral, indefinite integral, of 1 over 1 plus root x dx, right? And what I'm actually going to do first, I'm just going to rewrite this as tx over 1 plus root x. Kind of think of it as like multiplying by this dx at the end. Okay. So, what am I gonna make u here now? I think I will make it 1 plus root x. So I'm gonna say let u equals 1 plus root x here, right? Because when we differentiate this, we're going to get half of x to the negative half dx, right? And let's isolate for dx now, I suppose. So multiplying both sides by 2 and x to the half, not x to the negative half, just to cancel it out, we are going to get 2x to the half du equals dx. Okay, and notice I kind of kept it in this time, right? But we're not we're not fully done yet, because I don't particularly like this x here. So what I'm gonna do up here, back up here, is I'm going to rearrange kind of for root x here, right? Because this is sorry, this should be positive. This is just root x, right? So I'm gonna say u minus 1 equals root x. So now we can sub this u minus 1 for root x down here. Okay, so 2 u minus 1 to the half du is dx. Okay. So now we can kind of say right? We can replace that for dx, right? Here. So, whoops, I'm actually just gonna go ahead and write it now. Therefore, the integral of dx over 1 plus root x equals the integral of a dx over, sorry, I'm just writing the same thing. So now, if you think about it, we let this be u, right? So if that is 1 over 1 plus x, root x, dx, we could say that's 1 over u, right? So let's write that down then. 1 over u, or like u to the negative 1. And then dx. What do we say was dx here? We can set that in, right? So this is your next option. This isolating for x or root x or whatever it might be up here. That's like your second option if regular u substitution doesn't seem to work. If not, then you can't solve the integral by u substitution, right? You're not going to be able to find every indefinite integral using this method. There will be some that it just doesn't work with, but you will learn other methods. This is just an intro. I really don't have time to go over all of that right now. So we're gonna write in what we found to be dx. We're gonna sub that in for dx, right? So that's 2 u minus 1 all to the half. Actually, it's no longer to the half because we said, because we said that it's equal to root x, right? Root x is x to the half, right? And we already had the x to the half, so it's just that. My mistake. Okay, so dx, sorry, du. Okay, and so, well, now we can kind of like organize this. So that's 1 over u. Well, it's actually 2 u minus 1 over u. Right, and by du. Okay, and we can move this 2 over to the front here. So 2 times the integral of u minus 1 over u. Okay, and du here. So we can kind of break that up now into u over u minus 1 over u, and it's by du, right? And u over u is actually just 1, so I'll just write that down now. Right, it's just breaking it up. And so now, let's say 2, and we can compute this now. So 1, we said was just gonna be u, right? Or just the variable itself, right? And this 1 over u here is a little bit trickier, but it's still kind of simple. It's going to be the natural logarithm. Remember, I mentioned it before briefly in the antiderivative rules I had up there. But yeah, it's going to be the natural log of the absolute value of u, because the domain of the log function, it can't go past, like the log functions look like this, right? Where this is 1, right? It's never, you can't have a negative input for a log function, so we say the absolute value of u. And of course, plus c, can't forget it. Okay, now we just sub x back in, and we're done. So 2, and then I believe I made u 1 plus root x. Yeah, 1 plus root x. 1 plus root x, oops, 1 plus root x minus the natural logarithm, or ln, of 1 plus root x. And that's all plus c. Okay, so that's integrating by u substitution in a nutshell there. I'm going to give you guys a fun practice problem to take home. You can leave your answer in the comments, actually, and I can see if you guys got the right answer. So that's D, not E. We only got through 3. So D, I'll say the integral of x squared minus 1, or indefinite integral, over x cubed minus 3x dx. Okay, so take that home, try and solve it, and leave your answers in the comments, and I'll reply to them, ask or confirming whether or not you were right. So without further ado, that concludes the High School Math Fundamentals mini-series I had going on there. And I hope you guys found this especially helpful, or you do find it especially helpful when you guys go on to university. It's sad to see you guys leave O'Connor, but yeah, best of luck in your future endeavors, guys. Bye-bye.